Electric power systems are going through a major revolution right now. And with all of those electric motors powering just about everything from cars to boats to whatever, one trend is abundantly clear. Voltages are going up. And that, my friends, means we're going to need some transformers, of course. But with those high voltages around, we're also going to need to watch our clearance and creepage. And no, by creepage, we're not talking about that one guy your sister dated. You know the one. And some high voltage would have come in handy with that guy. Anyway, we're talking about maintaining the right amount of distance between conductors and... All right, well, let's just let my guest explain, shall we? Hi, I'm Amelia Dalton, host of Chalk Talk. Today, my guest is Cathal Sheehan from Borns, and we're going to take a deep and interesting dive into transformers for high voltage applications. Make sure our creepage and clearance are all good, and get ourselves ready for our next high voltage design. Let's go. And before we get started, don't forget to click that link. There you can find even more information about magnetics for high voltage applications from Borns. Hi, Cathal. Thank you so much for joining me.
Hi, Amelia. Thank you very much. It's a pleasure to be here.
Okay, so we're talking about magnetics for high voltage applications today. But before we jump into the details, Cathal, what specific magnetic products are we going to be talking about today?
Yeah, Amelia, today we're going to talk about two categories of transformer. The first category is talking about transformers which provide power in a high-frequency converter. And the other one then is a transformer which passes high-frequency data. And in both cases, the power and the data, we're transferring them across an isolation barrier. So the power transformer I'm going to talk about is called the HCT series. HCT means high creepage transformer. And the other then will be from our SM91 series of BMS transformers.
Now, I know that there is a growing demand for high voltage energy these days, but what do you see are the biggest factors driving this demand?
We see a lot of interest now in using alternative forms of energy in areas like, for example, underground mining. So instead of using a high horsepower internal combustion engine in an earth-moving equipment underground, we're seeing moves to replace that with a very high power alternative energy system comprising of high voltage batteries and ultracapacitors. Another area would be in the area of public transport, again recurring high voltage, moving up to areas such as 1500 volts. So there would be the main areas, I think, alternative forms of transport and underground mining.
So if we're going to be talking about high voltage applications, we also need to talk about isolated power applications as well, right?
Yeah, absolutely, Amelia. When we talk about isolated power applications, in this particular case, we're talking about transferring low voltage DC across an isolation barrier to power things like gate drivers, for example, for circuits like three-phase bridges, inverters, DC-DC converters. These devices need the low voltage to be able to drive them correctly. They need 15 volts, they might need -5 volts, and they need that to be able to turn on a gate, for example, it could be an IGBT or it could be a silicon carbide MOSFET. And it also needs to be able to turn off the gate. So you need to apply a negative voltage for that. So that's what I mean by isolated power applications. Not necessarily high power, but it's transferring low voltage from the low voltage side to the high voltage side. So if we consider the inverter on a DC to DC converter using, again, a bridge configuration, the gate driver would need 5 volts on the safe side of the barrier, and it would need 15 volts and -5 volts on the high voltage side of the barrier to be able to control the high voltage switching device. So generating the 5 volts on the safe side of the barrier is quite straightforward. You can use a DC-DC buck converter and some catalog inductors as well, which Borns does supply. To be able to get the 15 volts and -5 volts to the high voltage side of the barrier, then you're going to need to use a power transformer like our HCT series as shown on this diagram here, which we will talk about later, but which has the necessary mechanical characteristics to be able to operate in such a high voltage environment.
So, what would this look like in a high voltage battery management situation?
It needs power, but it also needs data. So in a typical system, as shown in this diagram, you've got the cells of the battery on one side of the high voltage barrier, and then you've got the communications line and the low voltage DC supply on the opposite side of the barrier. So the cell monitoring ICs require low voltage power, and it also requires a means of transferring the data from the cell measurements across the barrier to a central control unit. So in that sense, you need both isolated power, you also need isolated data, and that's kind of where those two would come into a high voltage battery management system.
So, where are we going with all of these types of applications, Kahal?
I suppose we talked about battery management systems, and we also talked about high voltage inverters, but you can see that the combination of power and data across an isolation barrier that can be used in other applications. For example, an industrial motor drive that might have a high voltage motor drive, but it would also have sensors as well, for example, that need to pass their data across an isolation barrier. In that particular case, the isolator which takes the data, that needs power, both on the low voltage side and on the high voltage side of the barrier. Also, for example, it could even be medical equipment, which is using a communications bus like the RS485. And the RS485, the transceiver for that or the isolator for that also needs power on both sides of the barrier. In all of these cases, you need a transformer like the HCT series to be able to easily and cost effectively transfer power across the barrier.
So, Kahal, it seems like having all of those insulators play nicely together would be a big deal here. What are the key issues we should be looking at when thinking about the insulation part of this?
I mean, the coordination of insulation for a high voltage system, that's really all about meeting the industrial standards for safety and insulation, namely IEC 60664 and IEC 62368. And what I mean by that is in terms of the materials you use for solid insulation, and then also the physical geometries as well in terms of the actual distances between the high voltage and the low voltage circuits. To comply with these standards, then, we require a certain amount of information about the system. So the peak working voltage is a very important piece of information. The overvoltage category as well. So that basically defines the maximum transient voltage that the system would see. The altitude as well of the application above sea level, that's also very important when you're designing your insulation. And then finally, the level of insulation as well. There are various levels from no insulation whatsoever right up to the highest level of insulation, which is called reinforced insulation. So all of those things are important when you're defining the actual insulation yourself. And that would apply both for the system and also for the transformer.
So let's talk a little bit more about that clearance you have at the bottom of the slide.
Yeah, so the insulation itself is defined by things like creepage and clearance. And the clearance is in a transformer, that's going to be the line of sight across air between the high voltage and the low voltage sides of the transformer. This is a physical distance and it's defined by the different standards I mentioned, IEC 60664. And in order to actually determine if the transformer meets these standards, there is a test defined by IEC 60664. It's called an impulse test. And that consists of using a piece of equipment called surge equipment. This surge equipment is connected to the primary side of the transformer, and a surge is applied to the primary side. The amplitude of that surge is defined by the standard IEC 60604, depending on the information already provided, i.e. the peak working voltage, overvoltage category, and etc. That's one very important test to determine if the clearance is correct or if it's not correct.
So tell me a little bit more about testing this solution.
The actual surge test is really to see if the clearance, which is the physical distance across air, meets the requirements. And that particular test is very, very short. It's only 50 microseconds. So it's a really very short test, but it's enough to determine if the distances are correct. Now, if you want to make sure if the actual solid insulation inside your device is correct, the solid insulation is the material which is wrapped around the coils inside the transformer. In order to make sure that that insulation is up to scratch and meets requirements, there is a different test. It's a dielectric voltage test. And in this scenario, we apply a high voltage, the value which is given in the standard IEC 60664 again, and we apply that for a minimum of 60 seconds. So it's a kind of a longer term test, and we wait to see if the insulation will break down. And we are able to check if it breaks down by measuring the leakage current between the primary side and the secondary side. So this dielectric test goes by many names, but the most common name is high pot test. That's how we make sure that the solid insulation meets the standards.
So I would imagine with these types of systems that testing would also need to be a long-term thing as well, right?
Yes, absolutely. When you design a system, you want to make sure that the insulation will last a long time. You don't want to have to replace the insulation after a shorter period of time. And one phenomenon which can happen in insulation, and which does happen, especially insulation which is subjected to a high electric field, is called partial discharge. So this is something which doesn't necessarily mean a failure. It's a kind of a phenomenon which happens when there's little tiny pinholes in the insulation, and over time the pinholes can expand and cause a complete breakdown of the insulation itself. So there is a test defined by the standards, and it's called the partial discharge test, where you measure the actual amount of discharge that's happening. The level of discharge has to meet the levels defined in the standard. This is a test which is mandatory for high voltage systems, and it's a test which we do in Bournes on our transformers.
So earlier mentioned creepage. Can we talk a little bit more about that?
Absolutely. So, I mean, if you were to design a transformer for a system, a high voltage system, and you had to meet a requirement for meeting those standards, one of the first things you have to check is the creepage, which again is the minimum distance between the high voltage and the low voltage side. This image actually shows what a power transformer could look like if you wanted it to be both low profile and SMD, and if it had to meet quite a high creepage. The red line there across the black plastic is the creepage between the pins and the core itself. If you've got reinforced insulation and you've got insulated wire on both sides of the core, then the total creepage would be the sum of those two distances, the sum of those two red lines. If you look at that image, I suppose you can see straight away that it's quite elongated. And when it's a surface mount device, that can cause issues such as, for example, coplanarity, because the plastic could bow quite easily. So it's very hard to guarantee that it's going to sit properly on the board when you're doing your reflow soldering. As well as that, of course, it does take up physically a lot of space on your board. So it's quite an awkward looking solution.
So, Cahal, if we want a magnetic device with low profile in a surface mount package with high creepage and clearance for high voltages, we're stuck with coplanarity problems as well as space issues, right?
Well, there are solutions. For example, our HCT series of transformers, if you can make use of the space of the actual surfaces on the transformer, then you can actually reduce the form factor of the device. The creepage is the shortest distance between the high voltage side and the low voltage side. But if you make use of the surfaces of the transformer itself, for example, to wrap the wire around the outside of the case, and then if you also make use of the actual lid itself on the device, then you can even increase further the physical distance over the surfaces of the housing between the high voltage side and the low voltage side. So there are ways of doing that.
Okay, so Cahal, can we talk a little bit more about creepage and clearance? How exactly do they work together?
This slide shows a cross-section of the HCT transformer, and it shows a cross-section of the core itself. It shows the primary side and the secondary side, so on the left and right. It's the shortest distance between the primary side and the secondary side, and that's going to be the distance between the two pins. And then the creepage is the shortest distance between the primary side and the secondary side over surfaces. Now, in this particular device, only one side uses reinforced wire, so that's the primary side. So therefore, the creepage distance will be the shortest distance between the pin and the actual core itself, as shown by the red line. That would be therefore the distance up the housing, then across, under the lid, and down the lid into the core itself. But by clever use of the lid and the wall of the housing, we're able to achieve the minimum distance of 8 millimeters creepage. So in this way, even though it's quite a low profile device, we're able to achieve a high creepage and a high clearance.
So how does the HCT series compare here?
The HCT series really makes clever use of the housing to achieve the maximum creepage and clearance of 8 millimeters. It also has a nominal height of 6.5 millimeters, so it's still a low profile device. It's a reinforced transformer. It means it can have a working voltage of up to 800 volts, which is really where a lot of the high voltage systems are at the moment, be they for industrial or automotive applications. We have provided this device with 11 different turns ratios, so 11 different part numbers. And Texas Instruments have approved this device for use with their push-pull drivers SN6501 and SN6505B. And finally, this is a fully approved automotive grade device.
So how exactly does the HCT work in a circuit, Cahal?
It's a compact device given the creepage and clearance and the high working voltage. And it's designed to work with the SN6501, SN6505B push-pull drivers from TI. So the SN6505 and this transformer, they are designed for high frequency converters, so up to 450 kilohertz, but with a minimum amount of EMI disturbance, so a very low EMI footprint. And the SN6501 is a SOT23 packaged device, so it's a very small device. And it does not need any extra components beside the transformer to work properly. Basically works at a fixed duty cycle of 50%, doesn't require any special feedback to work properly. And it's able to achieve its different output voltages thanks to the turns ratio on the transformer itself. So, for example, if you wanted to put 5 volts on a low voltage side of the isolation barrier and transfer that across to the high voltage side of the barrier to drive a chip, you could do that using the HCT series with a 1:1.3 turns ratio, which would take into account the voltage drops across the diode on the secondary side. And apart from that, you need very few extra components. So therefore, it's a very cost-effective solution for customers.
So if I'm looking for a battery monitoring solution that involves isolated communications, Cole, what all should I be considering?
When you're talking about a battery monitoring solution, isolated communications, we're talking about instead of transferring power, like in the HCT series, we're talking about transferring data. But we still have to consider a couple of things. First of all, the actual working voltage of the system. So as we said, some systems are now moving up to 800 volts, 1500 volts. The SM91501 and SM91509, these are both transformers which have a working voltage of 1600 volts according to IEC 60664, and they are functionally isolated. So that's the first level of isolation for a transformer according to IEC 60664 with a minimum creepage of 8 millimeters. So they are ideal for being used in the middle of a daisy chain of a battery management system where you're right in the middle of a stack. You're not necessarily too concerned about having reinforced insulation, which would be more important, let's say, at the entry point to the stack where the master is. Also, you'd want a transformer which is made to automotive grade standards.
So, Cahal, what are the most important things to keep in mind when choosing a BMS transformer?
I suppose one of the most important things is to remember that the transformer itself will be designed to work with different types of ICs. And some IC manufacturers might prefer to have a higher inductance value than others, depending on their chip design. So the open circuit inductance is a very important thing to check. And then as well as that, these transformers are operating in an EMI-rich environment, so the conducted emissions performance is very important. So another very important factor to check there is the common mode rejection ratio. And finally, also just to check which IC manufacturer has validated these chips. It's very important as well.
Okay, Cahal, this has been a bit to take in today. Can you recap your main points for me?
So we started off talking about high voltage applications. we've seen that areas such as, for example, underground mining, public transport are using a lot more forms of alternative energy at higher working voltages. Therefore, the magnetics that are used for providing isolation for power and data also need to be designed to the right standards, providing the right level of insulation, the right levels of creepage and clearance. And Borns has provided some transformers for power applications like the HCT series, for example, which have been validated by TI with their SN6501 and SN6505 drivers. And we've also provided the SM91509AL BMS transformer for high voltage applications, which has been approved by TI with their BQ79606 BMS monitoring IC. And finally, the SM91501 is a BMS transformer rated to 1600 volts, and this has been validated by ADI and NXP for their BMS ICs. So we have a good package of options for designers now looking to design systems requiring isolated power and isolated data.
Excellent. Well, Cahal, I think that's all I have time for today. Thank you so much for joining me.
Thank you very much, Amelia. I really enjoyed it.